dovresti andare in piedi così la telecamera ti vede.
Voglio evitare di rompere. Okay. So, well, thank you everybody. I'm Gennaro Romieri, the director of the Institute of Department of Physics at Torre Pancini. So I'm particularly pleased to welcome our distinguished colleague, Professor Damour. Professor Damour is coming from Paris. He's emeritus at the High Scientific Studies Institute in Paris. So very well known in the field of general relativity. So one of the biggest experts in this subject. And I'm pretty sure that this event, which is, by the way, the 14th appointment of this important series of Majorana lectures at our department. So just few words concerning our institute for our colleague, just few things, a few numbers. So our department is a quite large one in Italy, I would say among the largest one. We have over 200 staff members as a scientists, researchers, and many students. Here there are many PhD students and students of our course of physics. As an institute, is an institute interested in many fields of physics, so also in applied physics, experimental physics, and theoretical physics, of course. So order 100 laboratories just to have an idea of the size of our institute. So from this point of view, the theoretical activity, research activity in our institute is very large. I mean, is distributed in many research areas, and among them, of course, the part concerning cosmology and general relativity is very important. So for this reason, to devote a series of lectures, I mean the 14th Majorana lectures to general relativity is something very important and relevant for us. So I'm pretty sure it will be a very important moment, and so I wish that you will get profit of this important possibility. Thank you very much.
On behalf of the director of the NFN Naples section, Professor Lista, and of the Majorana Lecture Series Organizing Committee, I'm pleased to welcome Professor Damour as well. This series got started in June 2012 with lectures by Professor Riccardo Barbieri of Scuola Normale Superiore Pisa. We had several distinguished lecturers since then, including Luciano Maiani, former CERN director, Gerhard Tuft, Nobel Prize winner, Gabriele Veneziano, and many other distinguished speakers along years, until last year, lectures by Professor Witten himself from Princeton. So it's a point of growth of research in theoretical physics for young researchers and for more experienced researchers as well. So it has helped us in motivating our students and encouraging their full-time dedication to pure research in a series of fundamental interactions. So with this spirit, we are very happy to thank Professor Damour for his visit, and we look forward now to listening to his lectures.
Okay. Thank you. Thank you, Gianpiero. There are two announcements that I have to make. The first one is that when you want to talk and ask questions, you have to come here. We don't have our usual room, so we don't have the microphones that we can go around. Our usual room is being renovated. So if you want to ask questions, just come here and ask questions. The second one is even more important, of course. There will be a social dinner on Wednesday in the Pizzeria Brandi. For those of you that don't know, it is the famous pizzeria where the pizza margherita was invented.
And in order to participate to this event, you have to pay 40 euros, of course, but you have to sign on a list which is here, in which I will now circulate, and that's all. Now I give the floor to Professor Damour.
And don't hesitate to ask questions if there is something
I'm sorry?
Yes.
I cannot circulate the list because it's taped to the to the. So you have at some point, not, hopefully not during the talk, you have to come there and sign. Okay.
Okay, so I will start by introducing the mathematics of gravitational waves in general relativity, but first, also because the blackboard is so high that I won't be able to use the upper part, I have put for reference here the explicit structure of Einstein's field equations. So Einstein's field equations say that the stress energy tensor of matter, T mu nu, on the right-hand side, is the source of a nonlinear object which depends on second derivatives of the space-time metric. So G mu nu, in space-time gives the square of the distance between 2 points. It's in some coordinate system, it is described by this object. I will use a signature which is mostly plus, which means that when one is in the Minkowski flat space-time limit, the metric G mu nu is just a diagonal with -1 for time, +1, +1, +1 for space. Now, the explicit form of Einstein's equation is defined here. First, you define from first derivative of the metric here and the inverse metric, the so-called Christoffel symbols, or more precise, I mean, in modern terms, they were introduced by Christoffel, okay? And then Ricci understood for years how to define actually very good geometrical structures, and then Levi-Civita, the student of Ricci, understood later that there was a more general notion of connection, okay? That's why usually it's called now the Levi-Civita connection, so first derivative of the metric. Then from this, you define the Riemann-Christoffel curvature tensor, this object with 4 indices. And if you don't know this, just this object is made of first derivative of this gamma, which already contains first derivative of the metric, plus a term quadratic in this first derivative, and then you subtract from this the same quantities where you swap indices, these 2 indices, so that this object is antisymmetric in the last 2 indices. There is, if you don't remember how to write all indices, there is a simple way, which is that if you formally consider this object as a tensor, as a vector, that is to say, you consider that only the upper index is a tensorial index, and that the 2 indices below are not existing, okay? And you take what is called the Levi-Civita covariant derivative of this vector, which means you add to this object this term, okay? There is the ordinary derivative, and then the connection acting on this index here, contracted by sigma, define this. So it's a way to remember all this formula with more ease, okay? Then from this, when you contract the upper index and the one in the middle, this defines the Ricci tensor. This one, which is explicitly written this way. And then in Einstein's equation, you have the 2 forms, either the so-called Einstein tensor on the left, equal T mu nu, or if you solve for it, you have the Ricci tensor is equal to this combination of the stress energy tensor, where I kept the space-time dimension D arbitrary. When we are in 4 space-time dimension, this is T mu nu minus 1/2. but it is important when you work in any dimension to remember that there is a 1 over d minus 2. Okay, so at the end, Einstein's equation, the left-hand side contains second derivatives of the metric tensor, and is nonlinear. It contains, and we will see nonlinearities. But first, we start with linearized gravity to understand better this theory, and to see gravitational waves. So in that case, if I denote by eta mu nu the Minkowski metric, which means, okay, so the indices, yeah, mu nu, they go from 0 to 3. For 0, 0, this object is -1 on the diagonal, then +1, +1, +1. Okay, so it's a matrix diagonal -1, +1, +1. So this is the flat spacetime. It is a solution of Einstein's equation when the right-hand side vanishes, so for flat spacetime. And now linearized gravity means you look for solutions of Einstein's equation which are small deviations from, so it's mu and mu of x, and you work in first order here in this deviation, so small deviation, and you insert this here, okay, which gives gamma is linear in first derivative of h. Now you insert here, so you only need to keep these two terms, which are linear in second derivative. And then what you get is that the linearized Ricci tensor is equal to 1/2. This 1/2 comes from here. And then there is minus the D'Alembertian. So when an index is up here, I mean, yes, maybe I should say partial d with an index means partial derivative with respect to the coordinate x alpha here, x beta. So this is the D'Alembert operator, which means explicitly minus d0 square plus Laplacian in space. Okay, so here we have this wave operator acting on h mu nu, but it is not the only term. Then you have minus second derivative of h alpha alpha. So h alpha alpha means this is the trace with respect to the flat metric of h alpha beta. And then there are two more terms. Okay, so this is the linearized Ricci tensor. And if I look at waves in empty space, then from this equation, the right-hand side is 0, and therefore the wave equation gives this is equal to 0. Okay, linearized for gravitational waves. I should look for solution of this equal to 0. And now we will find general solutions of Einstein's vacuum equations at the linearized level by two different ways. First, as this is, it does not explicitly depend on the coefficients are constant in space-time, I can look for plane waves, that is to say, some amplitude, a tensor, and then a phase, which is a plane wave, where k dot x here means k mu x mu. So explicitly, this is k0, x0 is the time, plus k in space x, okay? If I introduce the frequency would be k0 up. Okay, most of the time, yeah, sometimes I put the velocity of light to 1 in order to avoid. Or if not, sometimes you want to say that x0 is ct, and then you put back c. I mean, or you never lose c, but sometimes I will not write c. So, okay, just to explain the notation. So it's very easy to replace this here, and then each term becomes a term here, and then you get the equation. This term gives k square mu nu, okay? Then you have k nu from the trace alpha alpha, okay, minus k mu k lambda a lambda nu minus k nu k lambda a mu lambda equal to 0. Okay. Now we want to find the most general solutions of this linearized Einstein equation with plane waves. And there is a simple dichotomy. So here I have not chosen coordinates in any way. Yes, I should have reminded you that Einstein's equations are covariant under changes of coordinate system. That is to say, they express the same physical properties in any coordinate system in space-time. And at some point, I have to choose a specific coordinate system because otherwise the general solution of Einstein's equation contains the arbitrariness that you can always change coordinates, so you cannot solve them uniquely. And we are going to see this here, okay. Now, I look for waves, okay. This is any solution, any tensor mu nu and any wave vector k mu satisfying this equation represent a solution of Einstein's equation. But now there is a dichotomy. Either k square, so k square means eta mu nu, just to be clear, means eta mu nu k nu. This is the notation k square, okay? Either k square is non-zero or k square is 0, okay? If k square is non-zero, I can solve this equation for mu nu, okay? And then, as you see immediately, what you get is that mu nu is a sum of terms. It's this term divided by k square, this term divided by k square on the right-hand side, minus this term divided by k square. But as you see, when I do this, there will be a k nu, there will be always either a k mu or a k nu. So if you, in this case, what you get is that the general solution of this is of the form k mu b nu plus k nu b mu, yes, where, for instance, b nu is equal to this object divided by k square minus 1/2 of this, okay? You just look at it, okay? It's just saying mu nu is a linear combination of k mu and k nu. But now one has to remember that, as I just said, Einstein's linearized equations are invariant under so-called coordinate transformation. If I do a coordinate transformation in space-time, it means that at this level, I am changing coordinates by new coordinates, like instead of, yes, I have to check in which form. X mu, I change to new coordinates x prime of mu, which could be any function of the original x mu with an index mu, okay, with any index here. So 4 functions of 4 variables. If I look for coordinate transformation which are very close to unity, I can write them as x mu, which would be the identity, plus a small quantity, psi mu of x, which I considered to first order, okay? Now, if you do this transformation and you say, I must conserve the square of the distance between 2 points in space-time, you find that the metric, this metric, after I subtract the flat space-time, is h mu nu as function of x minus d mu psi nu minus d nu psi nu, where psi nu is obtained from this by lowering the index by eta mu nu. Okay, so this is true to first order. If I look now at psi mu, which is a plane wave, so if psi mu is itself something with, let's say a coefficient psi at mu, which is now an exponential ikx, okay? this derivative will generate something which is proportional to k mu times psi mu hat plus k mu times chi mu hat. So now it means it will generate something like this. In other terms, this term is just the effect of a coordinate transformation. And therefore, when k square is different from 0, I can absorb, this is a solution of Einstein's equation, but it's a solution which is still flat space-time in a slightly different coordinate system. So it's a direct way of saying that in the dichotomy, either k square is 0 or not 0. If it is not 0, I am describing a trivial solution which is flat space-time in coordinates that are traveling like waves, and therefore it's not a real wave. It's just a coordinate wave. Okay. Conclusion, if I want a physical solution of Einstein's equation, I have reached the conclusion that k square must be equal to 0. Okay? But now, now this term is 0, and now I still have a condition that this term, which now is of, okay, the sum of all those terms must vanish, okay? And this term is of the form, this form, k mu times a certain vector plus k nu times a certain vector must be 0. And now if I solve this, immediately I see that this vector must be 0, which means that this vector, which includes 1/2 from this term, must be 0. So the conclusion is for gravitational waves, I must have k square equals 0, which means what? So we remember that eta mu nu, the Minkowski metric, defines a metric in flat space-time, which defines a light cone, and k square equals 0, which is eta mu nu equals 0, means the vector k mu, when considered as a direction in space-time, is along the light cone, okay, satisfy this quadratic equation. So this means gravitational waves propagate at the velocity of light, okay, that their wave vector is along the light cone, like for Maxwell's equations. But I get an extra condition that these three terms now must vanish. And actually what this gives, I have the other condition that k lambda, when you write these two terms, you get k lambda a mu lambda minus 1/2 of k mu times a, where a now is just a notation for the trace. So a alpha alpha, which is the trace of a, I just call it a, okay, is must be equal to 0. So I have the condition equal 0, which is equivalent to k lambda times a bar mu lambda equals 0, where I have defined a bar mu nu is a mu nu, this term, minus 1/2 of eta mu nu, the trace. Let me put again the indices. So if I, starting from the amplitude, tensorial amplitude, I define this quantity, I get the condition that this must be 0. Okay. Why am I explaining this? Because sometimes there is a kind of confusion. We see that gravitational waves in vacuum, not only they are described by a k which is on the light cone, but the amplitude must satisfy this polarization condition that as a tensor, this tensor, okay, is a tensor which is made of vectors orthogonal to k mu. So let me remind you of some geometry in Minkowski spacetime. In Minkowski spacetime, when I have any vector in spacetime, I can look at the set of all vectors which are orthogonal to this direction. And in the case where this vector is, okay, if the vector in spacetime is, let's say, in time, the orthogonal directions are in space, like this. All the vectors in spacetime orthogonal to any vector in time is like this. If I have a vector which is in space, okay, time for me means direction inside the light cone, and space means direction outside, okay? If I have a vector which is in space, all the orthogonal directions are like this. And in these two cases, the set of directions orthogonal to one vector in a four-dimensional space-time is a linear space with 3 dimensions, okay? But now, when the vector k is null, the set of null directions, the set, sorry, of when k is null, that is to say k squared equals 0, the set of vectors k mu such that k dot v is equal to 0 includes k itself. So the orthogonal space to vector k mu must be tangent to the light cone and contains, it's still 3-dimensional, but it is spanned by only 2 independent vectors besides k mu. Okay. So at the end, this is saying that this tensor is made of the tensor products of vectors which belong to this space, which is orthogonal to k mu. Okay. Now, there is a different way of reaching the same conclusion, but here I have not chosen coordinates. Yes, so the important point is I have found that this polarization condition must be satisfied without imposing a priori any condition. And by the way, if you do the same exercise for Maxwell equations, okay? For Maxwell equations, you would do the same exercise. You would say I have f nu nu equal d mu a nu minus d nu a mu. And then you would write the vacuum Maxwell equation like d mu nu f nu nu equals 0. And then this would give, this term would give, you know, minus d nu a mu from this term, plus d nu a nu. Okay? And then you could do the same thing. If I look for plane wave, these terms would give k square a mu from this. Because of the I, the minus sign disappears, minus k nu a nu, okay, equal to 0. And again, you would have the same dichotomy. If k square is not 0, a mu is proportional to k mu, but this is a gauge transformation for electromagnetism. And therefore, a general electromagnetic plane wave must have, like this, k square equals 0. But once you know that k square equals 0, otherwise it's only trivial solutions, you get an extra condition, which is that this thing must be 0. So electromagnetic waves are characterized by k square equals 0, plus the extra condition that k nu a nu equal to 0, which means that the amplitude a hat, okay, so here, I should write small a, yes. So here I have written that a mu is small a mu exponential ikx, okay? So I get for free the condition that the amplitude vector must be orthogonal to k, okay? But, so you see, often in textbooks you would say, let's use the Lorentz gauge, let's work in a Lorentz gauge, which in that case, the Lorentz gauge, by the way, and as people notice, the Lorentz or the Lorentz gauge should be with Z. It's not the famous Lorentz with TZ. It is another guy called Lorentz who also worked in electromagnetism. Lorentz gauge would say, I impose from the start that d mu equals 0, which would mean this transversality condition. And then the reasoning would be different, because if first you go to Lorentz gauge, then this term would not be there. And then you get the condition that k square a mu is 0, and then you get k square equals 0. But you see that you don't need to go to Lorentz gauge, because electromagnetic waves must be, actually, in a sense, in Lorentz gauge. And in the same way, gravitational waves must satisfy this polarization condition, okay? And so this is for electromagnetism. For gravity, I could also impose the analog of the Lorentz gauge, which has various names. So the analog of the Lorentz gauge for linearized gravity, for linearized gravity, the analog is like d nu of h mu nu minus 1/2 of h, the trace, let's say h alpha alpha eta mu nu, equals 0, which with this general notation would be that d nu of h bar mu nu is equal to 0. This gauge actually was used by Einstein in 1912, okay, before he even invented general relativity. And at the time, he called it, like mathematicians called it, which is isothermal gauge. And this is a name that I have seen in my youth in the books of Lichnerovitz, for instance. It is still used sometimes, okay? Then other people after Einstein rediscovered it, in particular de Donder and Longchamp. So some people call it the Donder gauge. Then later mathematicians said isothermal is not a good name. Let's call it harmonic gauge, because this gauge is equivalent to say that the coordinates satisfy a wave equation. And now mathematicians have changed their mind. They don't call it harmonic gauge. They call it wave gauge, because each coordinate is like a wave. Okay. Okay. So this discussion may be uselessly complicated, but just to say that if I first go to harmonic gauge, that is to say, now I say, I use the freedom of changing coordinates to impose this condition before looking for solution of Einstein's equation, then if you do that, you will see that this term cancels half of this term cancels with half of this, and the Ricci tensor, then in this gauge, the linearized Ricci tensor, linear in harmonic gauge, is simply equal to minus 1/2 the flat space-time D'Alembert to h mu nu. So now we see in harmonic gauge, indeed, I have the wave operator, and therefore I find now that k square must be 0 for plane wave. But you see the logic is different, okay? But the result at the end is the same. Okay, now let me mention two things about this. Is for Maxwell, so we have found that electromagnetic waves, if they are plane waves, you have the wave vector k mu, which must be along the light cone. Then the set of vectors k, v, which are orthogonal to k, as I said, is the three-dimensional hyperplane, which is tangent to the light cone, and therefore which includes the vector k mu itself, and then two other possible vectors, because in this, evidently, when I'm drawing things, I have one less dimension than one I should. This should be in 4 space-time dimension, and therefore what is a plane which looks like 2 dimensions has really 3 dimensions. So here, let me introduce, yes, just a notation for this. Here I can have 2 real vectors, E1 mu and E2 mu. Okay, so in this space, in this plane, I have K, and then I can introduce 2 solutions, A1 equals 0 and vectors equals 0, which are different from K mu, okay? So they are orthogonal to K, but they are not equal to K, or proportional to K. And then they span this space. The most general electromagnetic wave here must be orthogonal to K, so it means the most general A mu for a plane wave is a linear combination of E1 mu with some coefficients, C1 E1 mu plus C2 E2 mu. Now, as we know, there exist linearly polarized waves. If you take a solution of Maxwell equation, now plane wave, which is along one real vectors, I take this E1 and E2 mu as real vectors, then this defines a linearly polarized electromagnetic wave, okay? In in usual ways of seeing if I use a coordinate system, you know, x, y, z in space and then t, and I am going in some direction, if the wave goes in the direction z, then these two vectors, I could put them in the x or the y direction, okay? And then if I take only a wave which is along x, this is saying in the usual electromagnetic way that I have a wave propagating in the z direction and I have a linearly polarized electromagnetic wave going in the x direction or in the y direction. Okay. But I can also consider a circularly polarized wave. What is a circularly polarized wave? It is one which is of the type for electromagnetism. Mu is some coefficient, epsilon mu exponential ikx, where now I define epsilon mu as being proportional to E1 plus I E mu. So if I take a polarization vector, which is not a real vector, yeah, I should have said that these two real vectors, I also normalize them. I take E1 square equal to 1, E2 square, so unit vectors, and orthogonal to each other, E1 dot E2 equals 0. So I take two vectors in space, like x and y, which are unit vectors orthogonal to each other. And then I take the complex vector like this, with a plus here. This is a circularly polarized electromagnetic wave with some helicity plus, okay? And if I take a minus, the helicity will be minus, or the reverse. We are not going to worry about sign. Why am I saying this? This is just to remind you from electromagnetism. But now, this is, so it's a circular, so this is a circular plane wave. What is the analog for Einstein's equation? Circularly polarized. First, the general Einstein equations would be also, yes, will be the set. So I said that a general wave is of the form an amplitude and then a tensor epsilon mu nu exponential ikx, where epsilon mu nu, yes, now I need to say something else. Yes. Here, I could choose E1 and E2 in a specific way, because if I do a gauge transformation, electromagnetic gauge transformation, it means adding to a mu something which is d mu of a certain function of lambda, a certain scalar function, but this means to the amplitude a mu, I add something like k mu times lambda hat, the coefficient of the wave, okay? So it means a gauge transformation would mean that if I have a polarization vector which is anywhere here, I can add to it some linear combination of k mu, and then it describes physically the same wave, because it's just a way of doing a gauge transformation. So you can do the same thing for Einstein's equations. For Einstein's equation, I have shown here that epsilon mu nu must satisfy the condition epsilon minus 1/2 the trace of epsilon delta mu nu must be orthogonal to k nu. But I can still do a coordinate transformation of this type for Einstein's equation now, which is h mu nu, as I explained, plus d mu psi nu plus d mu psi mu, which changes its amplitude a mu nu by something like k mu psi hat nu, the coefficient of the plane wave here, plus k nu psi hat nu. So I can do a transformation of this tensor, which also changes this by this arbitrary 4 vector, okay? At the end, you find that the most general solution of Einstein's equation can be put also in a circularly polarized gravitational waves, which are described by an amplitude A2, which is the analog of the amplitude And then, sorry, yes. And a polarization tensor, and now this is the crucial point. I can choose, yes, this is for an electromagnetic wave. It is described, it can be described, circular electromagnetic waves, by a complex vector, which is the combination with I of two unit vectors orthogonal to K. If I take this complex Maxwell polarization vector for a circularly polarized electromagnetic wave, I take this, and now I take the product epsilon mu, epsilon nu. This object, epsilon mu, will satisfy the fact that epsilon, this is the contraction epsilon alpha. The trace epsilon alpha will be epsilon alpha times epsilon alpha will be the square of this epsilon. But this epsilon, if I take its square, it's a 4 vector. If I take the square of this 4 vector, I have E1 square minus E2 square plus 2I E1 dot E2. But as I said, I had selected E1 to be unit vector, E1 square equal to 1, E2 square equal to 1. So this minus this is 1 minus 1 is 0, and E1 dot E2 is 0. So this thing is 0, yes. So a polarization vector for a circularly polarized electromagnetic wave is itself a null, it's a complex null vector, so it's an epsilon mu, which is orthogonal to K, but which has a length square equal to 0, and it is orthogonal to K. So because of this, and now comes the conclusion, this epsilon square is equal to 0, so this term is 0, and then I get that the polarization condition I had obtained was that epsilon mu, K nu is 0, but if epsilon mu nu is taken as this product, epsilon mu nu times K nu, this is 0 because this was orthogonal. Okay. So this looks maybe a little bit strange, but the conclusion is, at the end, we see something very nice, which is hidden, okay? Which is hidden in the usual ways of textbook ways of discussing solution of Einstein's equation of Maxwell equation, that a general gravitational wave in Einstein theory is essentially obtained by the tensor product of electromagnetic circular waves. You see that, roughly speaking, a circular gravitational wave is like the product of mu c, nu c, okay? It is obtained by making the product of electromagnetic circular waves, by which I mean that the polarization tensor can be taken as the product. The amplitude also can be taken about the product, but I should not make the product of this. I mean, this is after factoring the exponential minus kx, okay? This is the amplitude, okay? After I factor epsilon minus ikx, I can say that gravitational waves is like the square of mu in u. I'm saying this because this is a fact which has been very important in string theory, and it has become an important motto, which is that Einstein is like the square of Maxwell, or the square of Young-Mills, actually. And here we see something simple, which is that the tensorial description of a gravitational wave can indeed be written as the tensor product of emitting electromagnetic waves. And this is very important in string theory and still plays a role now in modern physics. It's still mysterious, okay? It was discovered by Fubini and Veneziano long ago that the vertex operator for creating a graviton from a closed string is obtained as the tensor product. But you see that it has a simple source in ordinary way of solving Einstein's equation. Now, these were gravitational waves linearized and in flat spacetime. Let me go beyond linearized waves and tell you quickly what happens when you look for gravitational waves in curved spacetime. So when you do the same thing but in curved spacetime, here you should replace this. Maybe there is no color, but that's okay. Okay. You take a background spacetime, some spacetime B for background, and you say, I look for solution of Einstein's equation, which is a small perturbation from a given curved spacetime. And now you try to do the same thing, but then you cannot use plane waves because this is a curved spacetime. But what you can do is to do WKB. So for instance, what you can do is you say, I start from G mu and I look for solution with, and then I look for a wave which contains an amplitude and something like a fast varying phase, okay? So let me put it in WKB phi of x divided by epsilon, okay? A WKB, high frequency gravitational waves, would be some background, and here I need to take the real part of something which has an amplitude as a function of x and a fast varying phase. Okay, in WKB you would say exponential or cosine of phi divided by h bar, but here what is important is to have a small wavelength wave. So I look for a solution of Einstein equation where I have a background, and then on top of it I put something which is high frequency. So I will not redo the thing. What you can do is insert this in Einstein's equation and do the same thing, okay? In the approximation where you look at what is the contribution from a high frequency. And then the conclusion is that you find that gravitational waves, that if I define now, so this k dot x is replaced by the phi, and then k mu, which is the gradient of this, is now replaced by the gradient of the phase phi, okay? I will now erase something here to, to describe what happens when you consider strong gravitational waves, okay? Not only linearized, but possibly strong gravitational waves. So this is the thing, and I will do it here. Yes, probably I don't need this. Okay. So now we look for strong, high frequency gravitational waves. And I have 3 minutes. But I can say in 3 minutes the essential thing.
You can also go over the 3 minutes.
Okay, so let's give me 5 minutes. This way we can go to something else. This was first considered not in gravity, but in general PDEs by Leray, by actually Gording, Kotake, and Leray in 1966. In the gravitational context, it was considered by Dieter Brill and Isaacson in 68. And then Yvonne Choquet-Bruard has improved things by giving a more rigorous mathematical way. And I just want to describe the results without giving conclusions, without giving the derivation. So one is looking for solution of Einstein's equation, which depend on high frequency parameters. So now I take, instead of 1 over epsilon, I put a parameter omega, which is the order of the frequency, which it's a parameter which goes to infinity. And then you look for solution with some background d mu plus an amplitude. Let me explain this. X and omega phi of x plus omega minus 2 w mu nu times x and omega phi of x. You use what is called in physics two-timing methods. That is to say, you look for functions of two variables. Okay, this is a scalar variable, no indices, and these are 4 variables here, lambda. So you look for solutions that depend on x lambda and a variable psi, which is this variable. And you look for solutions where omega will go to infinity. So you don't assume here a cosine or a sine. You just take any function of two variables, but you make the other variables, which are going to go to very large values, as if it was okay, a cosine or sine, but you don't care. You look for now waves where the amplitude goes like the inverse of the frequency. And then when you do that, and you insert this in Einstein's equations, because there are two derivatives in Einstein's equations, okay, each derivative will bring a factor omega up, okay? And therefore, the terms with the highest powers of omega will contain omega squared from two derivatives and 1 over omega, which means that you have terms in Einstein equation which have of order omega to the +1. And then you ask the following question: what are the formal solution of Einstein's equation which admits a formal power series in omega minus 1? You know, I'm not assuming convergence, just formal power series. And you look at the field equation at the omega equal +1 level, and then it's exactly the same analysis that I have done here. You find that k squared, and you define k mu as the gradient of this function phi. So phi is the phase, okay, in space-time, the analog of k dot x. You find that the background, GB mu nu, okay, that k mu must satisfy this equation. Okay, it is null with respect to the background. So you have the same thing, but the background now, it is the cone of defined by GB mu nu. And you find this polarization condition that I had written here. You find that k nu times v mu nu minus 1/2 of v times g background mu nu equals 0, where v is the trace with respect to g mu nu. So it's the same analysis as before. But if you go to the next power, not omega to the +1, but omega to the 0, you get an interesting equation now where the Ricci tensor of the background, B, must be equal to, minus k lambda nabla lambda v prime mu nu minus 1/2 of nabla lambda k lambda v prime mu plus terms which contains square of v prime plus v double prime plus w double prime, where w is the next term, omega minus 2, that all this must vanish. Okay. And why am I saying that? I'm saying that because Garding, Leray, Kotake before, and many people had shown that if you do this for other PDEs, like in hydrodynamics or whatever, you find that this becomes, okay, these terms, if I could set them to 0, by the way, v prime means derivative with respect to the second argument, okay, d by d psi. So it's the derivative of this function with respect to this argument, okay? You find that this is a propagation equation, which would say that the propagation of this polarization vector along k, modulo a small term, if this term were absent, would be 0, which would be saying exactly what we found before, polarization condition. But when you do this for hydrodynamics, you find that these nonlinear terms, they change the profile. That is to say, if I have a strong wave, which is not a gravitational wave, but some V, which is some profile, okay, you find that this term stiffens the profile. That is to say, it can give a shock wave. That is to say, when this propagates, the thing becomes later like this, like this, like this, okay? You can have a wave, or you can have a wave which is like this, and then it becomes sharper and sharper. So for general PDEs, when you look for strong high-frequency waves, you find that they stiffen, and often, and in some cases, then they become, shock waves. There is something remarkable in Einstein's equation. I'm saying this because it's something that people did not understand even at the time where Isaacson was doing that. This was emphasized by Yvonne Choquet-Bruat, that Einstein's equations satisfy an exceptionality condition, which is that all those terms, actually, they do not stiffen the profile. And at the end, you find that the profile of the wave must satisfy this simple propagation equation. This equals 0, okay? And the effect of these terms is not to stiffen the profile, but to back react on the gravitational waves. That is to say, when you take all these terms into account, you find that the background is not what you thought. A background must satisfy an equation of this type. So you started from what you call a background. You put a high-frequency gravitational waves, and then you make it as high as possible with an amplitude which goes to 0, but just like the inverse frequency, which means that when you take one derivative of G mu nu, you will have one extra factor omega, and then you see that the derivative of this term is order 1. So in that sense, if I look at the connection, Levi-Civita connection, the perturbed part of the connection coming from the wave is as important as the Levi-Civita connection of the background. This, in that sense, a strong gravitational waves. And for the curvature, it's worse. The curvature of the gravitational waves is larger than the curvature of the gravitational waves, of the background. And you find that necessarily, I started from a, you see, we look for solution of R mu nu equals 0. Ricci equals 0. But you write a background plus a high-frequency gravitational waves, and at the limit, you find that the background actually must be curved. And this quantity, when you look at it, it is the energy tensor of the gravitational waves, okay? Which was first discovered by Isaacson, but Yvonne Choquet-Bruat understood better how to prove mathematically this. And the last point, before I stop, is just to say that this was done in 68, 69, and for a very long time it stayed like that. People say, okay, that's it, okay. Gravitational wave back react. But it's only quite recently in works by mathematicians in France, like Cécile Huneau and more recently by Arthur Touati, where, especially by Arthur, it has been shown that not only there exists formal solution of Einstein's equation as power series in omega, but exact solution. That is to say, you can define a rigorous sequence of, so you define a sequence of solution of Einstein's equation, sorry, depending on omega, satisfying Ricci equals 0, and in the limit, the limiting thing actually, when omega goes to infinity, this term goes to 0. The limiting solution does not satisfy Einstein's equation. It satisfies Einstein's equation with a stress energy tensor in the right-hand side. And it's a recent theorem of Touati. If you look on arXiv, you will find rigorous proofs of this, which shows that when you take the space of solution of Einstein's equations, which satisfy Ricci equals 0, there are corners where you take high-frequency waves where the limiting solution does not satisfy the vacuum Einstein equation, but contains something which physically is quite clear. Physically, it is saying, I have a background, and on the background, I have sufficiently high-frequency gravitational waves that they contribute to the energy by E equal mc square of the energy of gravitational waves. They curve space-time. Okay, let me stop here.
As I said, if someone wants to ask questions.
It's, yes, it's non-analytic.
Giampiero, if you ask people to come here, nobody will ask questions. So if we shout, the posterity will miss the question, but let's have a discussion. Otherwise, yes.
Possibly get that.
Okay, so I can repeat the question. Just so ask the question again. I was distracted.
The limit is non-analytic
The-
at high frequency.
Okay. I'm sorry, I have to repeat.
Yes.
Is the limit analytic in higher frequency?
No, indeed. In this sense, there is this kind of discontinuity that the limiting solution of Einstein's equations do not satisfy Einstein's vacuum equation. So in that sense, there is something, yeah, it's a singular limit, okay? It's something high frequency, but amplitude such that it contributes to something different in the limit. Yes. It's a singular perturbation theory.
I have a follow-up question. And since I'm here, I can ask. Oh, sorry.
You can pass
Is this because you have linearized at the beginning?
No. These are exact solutions, okay? It is consistent in the sense that at the level of the metric, this is still small. So this is this drawing, okay? You put something small but high frequency, and it compensates at the level of first derivatives, and it's even higher at second derivatives. So it's a delicate limit, yes. It's not uniform in the mathematical sense, and it has interesting features.
So the set of solutions is not complete. As a does it have some
yes.
properties of
yes.
smoothness
so
or
indeed
something?
you take yes. On the boundary of the space of solution of Ricci equals 0, Einstein vacuum equation, you have at the limit on the boundary, you have solution of a different equation. And then the question would be, here it's one particular way that we understand physically high frequency thing. But people have not fully explored what happens when you take very rough solution of Einstein's equation, when you take things, you know, in suborder spaces where there, I think it is still whether turbulence could exist, you know.
Possibly fractal solution will...
yes, it's part of the thing. Like in cosmology, there is the famous Belinsky-Halatnikov-Lipschitz thing where we think we understand what happens, but it's actually, I think, mathematicians for a long time said, let's stay what we understand, but now they say, haha, it's maybe interesting, just to open something.
Okay, Gaetano.
What happens if you do the same in the presence of matter?
So, good question. First, a simpler case is when you do Einstein-Maxwell, that is to say, if the content, energy content of the space-time is a Maxwell field, so the energy E squared plus B squared, let's say, of the Maxwell field, then you can do the same thing, but then something interesting happens, which is that you have, if you put both high-frequency electromagnetic waves and high-frequency gravitational waves, they transform into each other. For instance, you can have a space-time where somewhere you put a pure electromagnetic high-frequency wave, and then it will transform into a gravitational wave and then convert itself. So you have oscillations from electromagnetic and gravitational waves. And actually, there is also a work by Yvonne Choquebrua and Tommaso Ruggeri, who has studied the case for hydrodynamics, okay, for other types of matter where things are more complicated, because for Einstein-Maxwell, they propagate at the same velocity of light, and then they convert easily. In the general, I don't know everything. You should look at the book of Yvonne Choquet-Bruat, her last book, Einstein's Equation, where everything is discussed.
Okay, if there are no, of course there will be several more lectures. If there are no other questions, you have a question.
No, just curiosity, two curiosity actually. One is you said that it's very important for string this connection from the square.
Yes.
Why? Because one would have said in a string you have an infinite set of degrees of freedom. So how is related to simple to this simple case?
Yes, the simplicity for strings is the following. Let me write here. Is there are two types of strings, open strings and closed strings. Okay. Now an open string is an interval as ends. A closed string is like this. Now, indeed, if you quantize a string, you have infinitely many modes. Okay, starting from massless mode and then massive modes. Now, what I'm saying is important, especially for the massless mode. The massless mode of an open string is something like this. Its Regge trajectory corresponds classically to the fact that this string would rotate like this, where the endpoints would go to the velocity of light. Now, you can make from an open string a closed string as a picture by saying I take two open strings and then I attach time this way. And the same solution where the Regge trajectory, where the endpoints would go to the velocity of light, works for a closed string where I just, I attach two intervals like this and they go like this. And what is remarkable is that this corresponds to an electromagnetic wave. This corresponds to, this mode, this massless mode of a string is a photon, okay? This massless mode of a closed string is a graviton. And the fact that this is the square, you see it now pictorially. But if you look at the so-called vertex operator, which is how this couples our general string, you find that it is obtained by this tensor product. So it is deeply in string theory. But at the end, this is also something that one is rooted in ordinary physics. Okay?
You said that Einstein used this isothermal gauge, if I understand correctly, in 1912.
12.
So in which context did he use, since it couldn't be general relativity?
It was the context of pre-general relativity. You know that in 1911 in Prague, Einstein understood that he needed to have a theory with a metric G mu nu. And then he understood, he wrote, for the case where G mu nu is static as only the G00 component, he wrote nonlinear field equations. But then he said, I just got an offer from Zurich. It's good because my old friend Marcel Grossmann knows about geometry, and I will ask him what kind of field equation I can write for G mu nu. And then he came to Zurich with the idea of G mu nu, but not knowing what good equations to write. And Marcel Grossmann actually did not know this geometry at all, but he discovered Ricci, Levi-Civita, Riemann, Christoffel, and then he told him, look at this, at the Ricci tensor and this. And then in 1912, there is a notebook of Einstein where he's doing calculation every day. And then he says, thanks for Grossmann, I should write the Ricci tensor. So he writes the explicit form of the Ricci tensor. And then he tries to say, I have all those terms, but I want the wave equation, So how can I get rid of these other terms? And then he read the mathematical literature because he realized that the isothermal condition actually kills all those terms. But then he had a problem because it was not consistent with the conservation of T mu nu at the time. It was like, so he looked at this, he said, can I impose more conditions? He did many calculations, and then at the end he said, no, it does not work. We have to do the Einstein-Grossmann theory, which is less, okay? But he was very close.
Okay, I think we can go to the break. And thank again the speaker before that. We will reconvene at 12.
Abbiamo un caffettino. Sì, sì.
Infatti il terzo giorno adesso cominciano a dire, però ero spaventato perché dicevano 4-6 ore, invece è durato 3 giorni. Ciao, è piacere. Vabbè, dove abbiamo fatto il tipo del...
Sto andando al manicomio. Andiamo. Vabbè, arriverà. No, non ci sto venendo. La parte più, la parte con tempo curvo in 3 minuti, quindi va a scrivere una specie di serie, però diversa da quella che prima sempre, con frequenze, con ampiezze che andavano a 0. La prima serie dovrebbe essere questa di 9. Cioè questa, adesso non so se è una forma approssimata, intuitiva, perché lui poi ha fatto una domanda in professore e ha detto no, questa è una soluzione esatta. No, penso, e io negli appunti stavo scritto che approssima. Ok. Perché mi sembrava che stava scrivendo l'onda. Lui stava scrivendo un'onda in spazio-tempo curvo con un background generale. Cioè anziché piatto generale si sta. Non ci sta la omega nell'altro. E fin qua mi trovo. Lui ha detto poniamoci nel limite di omega che va infinito. E all'inizio diceva, ha scritto, poi queste espressioni devono valere queste posizioni, dovrebbe essere l'equivalente di questo, no, non è quello, è K4. Ah, è vero, sta mentre il secondo dovrebbe essere epsilon alfa alfa z. È la generalizzata. Il secondo quando fitti fatto espansione con queste condizioni e uscita il profilo dell'onda stringenza sì. Però poi da qua non so se stanno andando a registrarlo nel tempo, qui sono e da qua giustifico il concetto di onda gravitazionale forte, cioè che perché lui per le strutture inermi non risolvono più l'equazione del vuoto, ma risolvono quella con l'energia associata all'ora. Quindi c'è un team non esatto, però noi siamo partiti dal fatto che quello, cioè il Riemann non è RB, ma è quello quella metrica là, è zero. Però poi tu ottieni che quello del background non è uguale a zero, perché c'è un'altra roba in mezzo, ma quello del background è zero. No, tutto questo, il resto. Io voglio che tutto sia zero, perché quello è il prima. Il background non è zero, è quella la cosa. Non ricordo. Non è se l'altra parte con le omega da Riemann sul sinistro. Infatti c'è l'area del background più roba, dalla quella roba là. Però questa roba qua, io penso sia Riemann di G mini omega. Quello è zero. Però non è detto che RB è zero. Questo che stai dicendo. Cioè, io mi aspetterei, però perché c'è la io volevo capire c'era la cioè quei termini là sono stati, non so io, fanno quei termini là. Perché poi lui ha detto questi termini sono importanti perché dovrebbero dare la tua energia. Ho detto, però non l'ha scritto per la tua energia. Sì, non è si forma sul ci sta, non è nullo.
come ha fatto? Si è messo sulla sedia, vedi che ci sono le impronte. Ma per forza, effettivamente, ragazzi, io al massimo arrivo qua. Quindi non mi sembra molto più alto di me. No, eccolo qua.
What you were doing.
sociale dobbiamo fare.
Vado.
E come non può stare? dicono che c'è un altro archetto per chi fa le domande, in modo che glielo si dà a chi fa le domande senza dover spostarsi o senza
Però
essere
visto che
ripetere.
siamo molto compatti qua in zona, quindi come ha fatto prima
No,
l'altro chairman.
ma mi hanno detto...
Io posso darlo, non c'è
esatto, cioè se è prodotto un altro microfono, così tu lo puoi dare...
Ma c'è un parente che ha fatto Chloe.
È fatto?
Chloe,
no, è un omonimo, ma non è parente. Anche lui si chiama Bini, ma non è... Viene da Roma, io mi ricordo, diciamo, quando leggevi i risultati dell'esame, però sì, lo conosco.
Ah, cioè, siete pure coetanei?
Coetanei, proprio stesso anno, stesso... mi ricordo che si chiama Cesare.
Cesare.
Sì. Però non...
Domande?
Domande?
Possiamo iniziare? So Thibault, we can start for your second lecture. Maybe you can try to... Recommended, but maybe you can put on your head. It's okay. So you know the rules. You can interrupt at any moment, but we need the microphone. And so please, I will give you the possibility to interact with the speaker. Thank you, and we can start now.
Yeah, it works. So, we have discussed the structure of linearized gravitational waves. Now I want to talk about one of the formalism which has allowed to compute the generation of gravitational waves. So this formalism is a vast generalization of what Einstein did in 1918, where he computed the so-called quadrupole formula. So Einstein worked, it was the pioneering paper on how what is the connection between gravitational waves and the amplitude we were seeing when you have plane waves at infinity. You have this amplitude of gravitational waves. You want to relate this amplitude to the structure of the material source, which is generating gravitational waves. Einstein worked in linearized gravity and understood that if you make a multipole expansion, the first multipole which is emitted is the quadrupole. Gravitational waves are not generated as monopolar waves or dipolar waves, but only quadrupolar waves. And so I want to explain what means a multipole expansion, because we are going to introduce the multipolar post-Minkowskian formalism. Which is abbreviated as MPM. So multipolar means you decompose in multipoles. Post-Minkowskian means you start from, like we did before, the Minkowski metric. Then you go a first order beyond post-Minkowski. And then post-Minkowski, you have a nonlinearity expansion. So here we are going to combine the two. But let me first explain what is a multipole expansion. Okay. Multipole expansion means an expansion in irreducible representations of SO3, of the group of rotations in space. And I will explain in simple terms what it means. So first we will consider the simplest case where I have a field phi, a scalar field, which satisfies an equation of the type wave operator acting on phi in Minkowski spacetime. So this is the D'Alembert operator with respect to the Minkowski spacetime, equals some source. You know, like you write a source maybe with a minus 4 pi. If you have a function here of space and time, this is a function of space and time, and you want to write the explicit solution of this. We will do this, but first I want to explain what means invariance under rotations. Okay, this operator, so when I look at the wave outside of the source, so in space-time, the source would be somewhere in the middle of space-time. This is a space-time diagram with time going up and space horizontally, x, y, z. And then you have the source somewhere in the middle. Maybe it is a binary system, or it is going around or scattering, whatever. And then you look at the field outside of the source. This field satisfies D'Alembert phi equals 0. And because the operator D'Alembert is invariant under rotation, this means that if I take one solution phi and then I define a new solution, which is obtained by rotating the solution. So I have a rotation operator which depends on 3 angles, okay? A general element in SO3 depends on 3 parameters. So what means, and so I rotate the field phi, and I look at it at, so what it means, it is phi, I do not touch time, t, I'm doing a rotation in space, okay, at fixed time. And then it means I act the rotation, the inverse of the rotation on the point in space, because indeed what you want is that if you have a field which, as a function of the angles, for instance, is very big here and smaller on the rest of the sphere, you want to make a rotation such that the point where it is big is moved by the rotation. I make a rotation where this point moves here, okay? So it is an active rotation. And it is equivalent to rotating the source. They say, if the source was sending in some special direction, more importantly than the others, if I rotate the source, the solution will rotate in this sense. Okay, just to fix time, fix notation. Now, if I have any function f on a sphere, so now if I look, this rotation keeps in x, can be, the vector x can be decomposed in its magnitude and then a unit vector. And now the rotation keeps r fixed and rotates n. So if I have a sphere of the direction n, I take a function, a scalar function on the sphere. So function of 2 angles on the sphere. Now, what a multipolar decomposition means that there exists a unique decomposition of this, an arbitrary function. So I take a scalar function on the sphere. An arbitrary function can be decomposed in special types of functions of n, parameterized by an integer L, which goes from 0 to infinity, such that, for instance, in this decomposition, the L equals 0 part means constant on the sphere. It is an irreducible representation of the rotation group, which rotates into itself. Okay? L equal 1 would mean a particular function which looks like a dipole, which has a special direction, which I will rotate the dipole along the sphere. Now, a convenient way to define this thing is to write them. Okay, usually in textbooks, you would find that you must decompose FL in YLM, in spherical harmonics. Okay, sometimes it's convenient, but sometimes it is not convenient, and in a nonlinear theory, it is not convenient. And there is a better way, which is to use the symmetric trace-free decomposition of okay, it is a representation of the rotation group that I will explain, but in practical terms, it means that each term decomposed with L here is represented in this way. Okay, it is a polynomial in N. It's true that this thing is not very good. I mean, in the unit vector, polynomial in N with coefficients, which is a tensor. Tensor means tensor with respect to the group of rotation in 3 dimensions of the, let's say, R3 in the Euclidean space in 3 dimensions, with L indices, such that this tensor is symmetric. So all the indices are symmetric and trace-free, which means if I take any contraction, delta I3, let's say, and I5 of an object like this with I1, I2, I3, I4, I5, I make the contraction with this with a delta. This is 0, okay? So the space of symmetric trace-free tensors with L indices, if you think about it, it satisfies so many conditions that you find that this is a space with 2L plus 1 dimensions, okay? And this space spans an irreducible representation of the rotation group, which means that when I act with the rotation operator on this function, FL of N, so I1, IL, and I1, and IL, okay? This thing is obtained by rotating this tensor. This is a tensor with L indices. I rotate it by a usual rotation matrix. So this means now this acts like a rotation matrix. I should put, yes, okay. If I change the name of these things, okay, let me put this, and I1 and IL are acting on this tensor means I act with a rotation I1, J1 on the first index, J1, and I2, J2 on the second index, etc. So I make, this is now a rotation matrix satisfying, you know, R dagger equal the unit matrix. And this tensor rotates, each index rotates this way. Now, why is it useful? For instance, let me give you a simple example. L equal 1, the space of L equal 1 is described by a tensor with only one index. So this is a vector. It does not need to be trace-free. And then rotating this thing means rotating with just this rotation matrix. So if in this sum one term is just a vector linear in Ni, okay, this is a dipolar contribution L equal 1. Okay? A quadrupolar part would be Fij, Ni, and J with two indices, symmetric without trace. And this, now there are three. The space of vectors like that is three-dimensional. So indeed, it is 2L plus 1 for L equal 1. The space of symmetric trace-free tensor with two indices, you could think, okay, I have 3 times 3, but it is symmetric. So it's 3 times 4 divided by 2, which is 6 components. But I take away the trace, so it's 6 minus 1. So it has 5 possible independent components, which is exactly 2L plus 1 for L equal 2, etc. Now, why why it is useful for solving equation of this type. Let me describe. For instance, if I solve now not the D'Alembert equation, but simply the Poisson equation. Okay. What is the most general solution of the Poisson equation? First, it depends if I look at a solution which is regular at the origin or which decays at infinity. Let me, for instance, say that the general solution of the Poisson equation, the Laplace equation, Laplace of phi equals 0, which is regular at the origin, I can describe it as being sum over L equals 0 to infinity of C at L, X at L. Okay, let me describe this notation. Let me write it first. C at L, R L, N at L. Okay. It is very convenient when you have many indices like this, I1, I2, IL, to represent this by just one big letter, capital L, which is the number of indices. Okay, it's just a way, instead of writing, I1, Ij, you write just L equal to capital L. And this way you keep the information that there are L indices in the notation. Evidently, when L equal 2, you don't want to write 2, but this is for general L, it's convenient to do it. So this notation here means a tensor with L indices. Here, this means C hat I1, I2, IL. And this X hat means X, I1. It means also the product I2, X, IL, in which the hat means you take the symmetric trace-free part. You say you project this thing along the set of, you project it by a projector along tensors which are symmetric and trace-free. So it gives a simpler notation. Okay. Now, why is this a general solution of Laplace? Simply because it is very easy to check that if you take, for instance, if you take the Laplace of xi1, xi2, xil, okay, and when you take the Laplace operator, you will see that you generate a trace because you take one derivative and this becomes an index. It becomes delta I1 times I and delta I2 times I if you contract with derivative di. And then if you take it trace-free, you find that this is 0. Okay. For instance, this is trivial to see that xi is solution of Laplace operator equals 0, but you can also find that xi, xj minus the trace, so 1/3 of x squared delta ij. If you compute the Laplace operator on this, the Laplace on xi is 0, Laplace on j, you need the double product, which gives delta ij, so it gives the same thing as this, so you find that this is 0, and this is true to all orders. Okay, so the general solution of the Laplace operator, which is regular at the origin, has a structure like that. Now, we know that, so what you find is there is a function of the angles, which is this function, times RL. Okay. Now, one way to solve the Laplace equation is also to write that in polar coordinates, the Laplace operator can be written as 1 over R dr2 derivative times R acting on something, plus 1 over R squared, the Laplace operator acting on the angles, okay? Only on L. Now, what we have seen here is that R to the L is a solution of this equation, okay? This combination is a solution of Laplace equals 0. If you replace in this equation, you find that delta theta phi acting on n hat L is equal to minus LL plus 1, okay? And at L, just because I have proven it's very easy to prove this, so you prove this indirectly. So you find that indeed the product, so n at L, let me re-explain, is n I1 and I2. It is a tensor with L indices. this is symmetric, but I take away all tracers, and this is what I call a tensor, symmetric trace-free with L indices. So here I have proven this. Now, knowing that this satisfies minus LL plus 1, it is easy to find that another solution which would be not regular at the origin would be when R to the L is replaced by 1 over R to the L plus 1. Because indeed, this operator acting on this and this gives finally the same structure as LL plus 1 that I have here. So conclusion, the most general solution phi, which is decaying at infinity, is of the following form. It's a sum of L equals 0 to infinity of another coefficient, dl, and instead of n at L, R over L, it's divided by R to the L plus 1, okay, just by using this reasoning. Now, let me give another simple proof that this is indeed the most general solution of the Laplace equation which decays at infinity, which is even simpler than this proof, so it will prove this. I take 1 over R, okay. 1 over R, as we know, is solution of Laplace equal minus 4 pi, a delta function at the origin. But if I don't look what is at the origin, it is a harmonic function. It's function of Laplace of 1 over R equals 0. If 1 over R is an harmonic function, I can take a derivative with respect to I1 of 1 over R. It is also harmonic. If I take two derivatives, it is again harmonic. If I take L derivative, it is again harmonic. So evidently, these things are general solutions that decay at infinity of the Laplace operator. But when I consider this, let me remind you that instead of writing di1, di2, dil, I just write d capital L, where L is a symbol for making many indices like that. So dl of 1 over R is 0, okay? But if I take a trace with respect to any indices, so this means di1, di2. If I take a trace, it will generate a Laplace operator in the middle. But Laplace of 1 over R, sorry, it's not equal to 0. It's a solution of delta equals 0. But this thing is trace-free, okay? If I take any, it is symmetric and trace-free. And therefore, it must be proportional with some numerical coefficients to n hat L over R to the L plus 1, because if I differentiate 1 over R once, I have 1 over R squared, twice 1 over R cubed. So I see that the power must be 1 over R L plus 1. It must be symmetric and trace-free depending on the angles. And it is a solution of Laplace equals 0. So I have reproven in one line that n at L divided by R L plus 1, that this thing is solution of Laplace equals 0. Okay. Now, what I'm saying is that instead of saying, so these are called multipolar solutions. So here I have written general multipolar solution. I've taken a general solution, let's say, of Laplace equals 0 decaying at infinity, or here not decaying at infinity. And I have shown that a general solution of delta phi decaying at infinity can be written in this form. Its phi is a sum over L of some tensor d prime L dl of 1 over R. Okay? Where this is a symmetric trace-free tensor, or I don't need to say this because this is already symmetric trace-free, so if I contract it, it will project out all the traces, so I can take it symmetric trace-free. In explicit terms, what does it mean? Just to be more concrete, here I have written that phi, for instance, it's a sum over L equals 0 to infinity. L equals 0 means a certain coefficient, d hat 0, 1 over R. Then the next term would be a certain vector, di of 1 over R. The next term would be a tensor symmetric trace-free, dij of 1 over R, plus etc. Okay, so here I have decomposed the general solution of Laplace equals 0 decaying at infinity as a sum of terms, 1 over r. So this is a monopole. So now we call this a monopole, a dipole, a quadrupole, etc. So here I have not used YLMs, okay? But this is equivalent to decomposing in various YLMs. Now, those objects parameterize the solution outside the generic source. But now I want to relate those tensors here to the source itself, because we want to solve the field as a function of the source. So, for instance, here I'm going to consider, I'm discussing the Poisson equation because it is simpler than the D'Alembert equation, but we will go to the D'Alembert equation immediately. If I consider the solution, the Poisson equation, which is Laplace operator of phi acting on x equal minus 4 pi times a certain density in space, rho. The density in space being localized in some region. In this case, I can write the solution, okay? Because I know what is the Green's function for the Laplace operator. I mean, the solution of the Poisson equation is integral over a source point. So I have the source in space now with some points inside the source, and I have the field at point x here, phi at point x. The solution of this equation is the integral d3y of rho at point y, the source at point y, and the Green's function for the Poisson equation is Laplace of 1 over x minus y is minus 4 pi delta of x minus y, okay? And therefore, this is divided by x minus y. Okay, this is the well-known solution of the Poisson equation. And now let us see what is the decomposition in multiples. The decomposition in multiples in terms of the source means I consider that y, that x is outside, and I'm going to make a Taylor expansion in powers of y inside the source. So this means I must Taylor expand the function 1 over x minus y with respect to y. But what is a Taylor expansion? A Taylor expansion, if I have a function of y, and I Taylor expand, it means f of y equals 0 plus yy d by dy f of y, but taken at 0, plus 2 derivative, dij, etc. Okay, it means expanding in derivative with respect to y, okay? Therefore, this thing I must expand in powers of y, but this expansion is actually the sum of y to dl, okay? F of 0. In my notation, okay, yl means, you know, y no indices, y1 index, y2 indices, okay, etc. It's just a notation for the Taylor expansion. So here I have a minus y, so this thing decompose is minus L, because there is a minus L, y to dl, and then, yes, minus L, y dl, sorry, maybe the famous factorial L of the Taylor expansion. So I need to put factorial L of the Taylor expansion of dl, the derivative of x. So I take, sorry. Yes, sorry. When I do this, it's dl simply of 1 over x. Yes. I have expanded, let me write better. I have considered the function 1 over x minus y, and I have Taylor expanded it with respect to y, which is small, let us say, near the origin compared to x. So I have obtained this formula, which is exactly of the type I wanted, that is to say, the general solution of here, the Poisson equation outside the source is the sum of dl of 1 over r, which means this, with a certain coefficient, okay? And what is lacking in this formula, I still have the integral of d3y, okay? and I have rho of y. I have taken this thing out because I have expanded 1 over x minus y. Conclusion, I have obtained the following formula. Given the source of the Poisson equation rho, if I defined ML as integral of d3y, integral over the volume of the source of rho of y, y to the L, which means y I1, y I2, y IL, I symmetric, but then I take all the traces, which I indicate by the hat, so it's the trace-free part. Okay, I put it here. I define a symmetric trace-free tensor with L indices. So, for instance, M hat with 0 indices means integral of d3y of rho, so the total mass. M hat with 1 index means integral of d3y rho of y, yi, so it's the dipole. With 2 indices, it means I have yi, yj minus 1/3 of y squared delta ij, the symmetric trace-free part, etc. So I have expanded, I defined those multiple moments. And therefore, I have proven here, because these multiple moments, they appeared here and here, okay? They were not symmetric trace-free, but initially, but because this thing is symmetric trace-free, I can take this symmetric trace-free. And then I have proven that phi of x is equal to sum over L from 0 to infinity of those multiple moments, ML, sorry, let me put, minus L over factorial L, which came from this and Taylor, times this tensor symmetric trace-free, dl of 1 over r. Okay. So here in textbooks, you would usually find this in the form YLM, saying the general solution of Laplace equation is 1 over r L plus 1, a coefficient CLM, YLM. So this is equivalent, but why this is better is when you take YLM, you have to select, it means you have selected a z-axis that you had to select like this. Why here, you have selected no special direction. You have decomposed the solution in something which is the total mass, a vector which is the dipole of the source, a quadruple tensor without saying what is the z-axis, the y-axis, or whatever, okay? If you want to make the connection with the YLM, let me now explain quickly this connection. YLM of theta phi is a special, is an object which is I1, I2, IL, and I1 and I2 and IL, where this is symmetric trace-free, and therefore this thing is also n with product of n. The n is the unit vector with L indices, symmetric trace-free, projected in this thing, okay? The YLMs actually is a special type of symmetric trace-free tensors which depend on your choice of x, y, and z axis. This is why it's not good to use it when you do a general theory where you don't want to select a z-axis from the beginning or whatever. And let me actually just state that the YLMs are defined by taking, okay, so the YLMs are always a certain tensor with L indices, L, contracted with n at L this way. Now, in the YLM, if m is positive or 0, this tensor, which is here, is actually the symmetric trace-free product of the following vectors. Plus 1. Let me just say times E0 times E0. Let me explain this formula. I define a vector E0, which is, if I select a z-axis, which is Ez, and then I define E plus or minus 1 as a vector, which is minus or plus Ex plus or minus I Ey over square root of 2. So if I have three vectors, unit vectors, Ex, Ey, Ez, okay? I can make, like before, for the circular polarization, I can make complex combinations of Ex and Ey and Ez. So this is a null vector, which is of the +1 and minus type. If I take, okay, let me just state the thing. If I take m copies of this +1 vector, how much is this? 10. And if I take L minus, really? Then what you can prove is if I make the tensor product of m vectors of this type with a plus and L minus vectors of the E0 type, which means the Z direction, this is the YLM. Okay? So it's just explaining that YLM is a particular way of doing it. Now, why did I call this? I recall this because it gives you a simple understanding of the usual multiple expansion with the simple Poisson formula. Now, when we are doing gravity, we must solve not this equation, but this equation with the D'Alembert and a source which depends both on time and space. And we must solve it not only for a scalar, but for a tensor. So now, what is the result? If you generalize this, but to generalize this, you need to generalize the notion of having the 1 over x minus y. And then, let me give you the result. The result is very similar to this. So the result was worked out for the details. So now, you see, now I have this, let me write. I have this equation, 4 pi minus 4 pi, a function of x and t. So the source I call S. I look at the solution of the D'Alembert. And then I look at the solution phi at some point in space-time, which is obtained by now the retarded Green's function. So I would need, instead of 1 over r, take the retarded Green's function. But I need now to do the same type of expansion that we did, which was easy with the Poisson equation, for this. So it is slightly more complicated. One needs to start from the retarded Green's function, which is Tx, T prime, X prime, which is something like delta of T minus T prime minus X minus X prime, or Y. Okay, if I have, let me coupe X prime here, over C divided by X minus X prime. For time-independent cases, it was just 1 over X prime, but I need the retarded thing. I need to insert, and then at the end, you find that phi, the general solution, Tx, is equal to a sum over L equals 0 to infinity of the same type of formula, minus L over factorial L. Then what was happening here? What was happening here is that I had decomposed the solution of Laplace equals 0 in particular solution of Laplace equals 0. 1 over r is a solution. What is the famous solutions of the retarded thing? What we know is if I have a function f, the t minus r over c over r, this is a solution. This is a monopolar wave. This is a solution of D'Alembert equals 0. This is a solution which is retarded, decays like 1 over r at infinity, and which has a certain f. And actually, what you prove is that here I can write dl of f hat L of t minus r over c over, so which means x over c over x. So it is very similar to this. It is the Elf derivative. Finally, here I have the Elf derivative of 1 over r, and here I have the Elf derivative of a function of t minus r over r, which is a solution of D'Alembert equals 0. And then the analog of this formula, which was that the coefficient ml, okay, this formula I could have written this way also. The L of ml over r, okay? Here I have a multiple which depends on time. And then you get the following formula. What you find is that, so these are called the multiple moments for the D'Alembert equation with source, inhomogeneous D'Alembert equation with source. And you find that this FL, which are the multiple moments of the source, okay, as function of t, they are obtained this way. They are integral. They are given by the same type of formula. Okay, let me write it this way. D3y of S bar L of t and y times y to the L. So it is exactly the same formula, but now I can define what is S bar L of t and y. Here, this ml was simply the integral, yes, okay. Sorry, is an integral over z going from -1 to +1 of delta L of z, the source at time t plus z y over c, and y. Okay, so, and delta L of z is a certain numerical coefficient, 2l plus 1 double factorial over 2 to the power L plus 1 factorial L times, okay, it's a double factorial here, and this thing has 1 minus z squared to the L theta function of 1 minus z squared. Okay. So it has the same type of structure. You start from the source. You do an average over an extra parameter z, which goes from -1 to +1. The reason why you have to do this average is that you are decomposing the field here on a sphere, and then this field is a retarded field obtained by all the slices of the sources at some retarded times, okay? And when you do the computation, you find that this averaging over angles means you need to do this integral over time, that you shift time where z goes from -1 to +1, but this is the source. And then you take the usual multiple moments of the source, okay? So this is a basic formula, yes, which is the starting point for how to express the general solution. So next time I will write the formula that when you solve now Einstein's equations, and you need to solve now D'Alembert of h mu nu is equal in harmonic coordinates. I have said before that when I am in harmonic coordinates, h bar mu nu satisfies D'Alembert h bar mu nu equal minus 16 pi g over C4 T mu nu, okay? So you need to solve an equation of this type, precisely this type, and then you will introduce multiple moments of T mu nu, and then be able to write the general solution of Einstein's linearized gravity around the source in terms of explicit integrals of T mu nu. And next time we will discuss how we go beyond linearized gravity by taking into account all the nonlinear effects of gravity, which changes what happens, like tail effects and memory effects and all that, but by using this basic multipolar formalism, which, by the way, we had introduced with Luc Blanchet and Bala Ayer, okay? It's called the BDI formalism long ago, and this is the formalism which allows to compute the gravitational wave generated by a general source. Okay. So let me stop.
Thank you, Thibault. If there are questions.
Indeed, there is a formula. Let me write this formula. As I did not prepare it, maybe it will have, let me write it here. There are, if I look for a solution of a Green's function, solution of this equal some delta function, okay? There are several Green's functions. First, as we know, usually one goes to Fourier space and then write things in terms of Fourier space. And then there appears you need 1 over k square, now in space-time, plus or minus I epsilon. And if you want the retarded, the epsilon has to depend on the sign of k0, okay? Okay, just to say, in Fourier space. If you go to X space, there are several Green's functions. And one of them is actually 1 over x squared plus I epsilon. The real space Green's function corresponding to the Stueckelberg Green's function that some people call Feynman Green's function. I'm joking. It was introduced by Stueckelberg, but usually it's called the Feynman Green's function. It is 1 over x squared plus or minus I epsilon. One has to check depending on the signature. So this is a Green's function with indeed x squared. Now, if I take the real part, yes, sorry, the Feynman Green's function as an I. Okay. Now, if I take the real part of the Green's function, I can use the fact that I over x squared plus I epsilon, let's put plus or minus, is I principal value of 1 over x squared minus or plus I epsilon. And if I take the real, sorry, delta of x squared, okay? And therefore, if I take the real part of the Green's function, of Feynman's Green's function, I get modulo factor I pi, okay? I get something like delta of x squared. Indeed, the delta function for the space-time distance, okay? But now, if I take, I'm going now to answer your question. Delta of x squared means delta, if I change the signature, t squared minus r squared with the opposite sign. And this is the sum of two terms. This is 1/2 of delta of t minus r over r plus delta of t plus r over r. So at the end, indeed, the symmetric Green's function, which means 1/2 retarded, 1/2 advanced, is a delta function of the space-time distance square, but it can be written by just usual formula as 1/2 of the retarded. This is the retarded Green's function, and this is the advanced Green's function. So you see that hidden here, I needed to take the retarded thing. That's why I needed to take this, and I cannot use this directly, okay? Just.
Perfect. Other questions?
Causality.
Yes, this is causality, yes. This thing, we want the source to generate in the future, okay? In some of the other lectures, we will use actually the time symmetric thing, which plays an important role sometimes. But if we want the retarded causal thing, you need classically t minus r. there any double copy type relation between the multiple expansion of the electromagnetic source and the gravitational source? It's a good question. Not actually to see the double copy, one needed like circular type polarizations. When you do multiple expansions, you are far from using these special LECT projections. And because of this, when you look at the multiple expansions for gravity, it looks very much like the multiple expansion of electromagnetism, that you have a mass dipole instead of a charged dipole, okay, a mass monopole, a mass dipole, a mass quadrupole. You have magnetic type quadrupole and magnetic things like that. At this stage, you don't see any double copy thing, okay? But they are, okay, the double copy, we know it exists somewhere in some formulation, and it appears only for some observables, okay? Yes. But non funziona questo. Yes. Yes. Good question. Yes. I did not actually say it explicitly, but let me say it. When you apply the multiple expansions to this, you do get, but let me explain the results. You find that the general solution of Einstein's equation outside the source is parameterized by two infinite sequences of multiple moments, okay, which is the mass moments, the analogues of the positive parity, the usual, okay, electric parity multipoles, and the moments ML, they start at M without any indices, at a dipole, and then quadrupole, and then octupole, okay? But, so, the general solution of linearized gravity outside the source contains a mass, a dipole, quadrupole, and then spin types moments, which contain denoted SL, which starts with the spin vector, spin vector, a spin quadrupole, a spin octupole. What happens is you prove, and we will show it, that the mass monopole is the total mass and is conserved. The mass dipole is second derivative is 0. And because of this, in the gravitational waves where these come with L derivative, okay, this will disappear. The dipole, because it has a second time derivative which is 0, does not emit energy, okay? But it exists, okay? If you have a static source, you have a mass monopole, the total mass, a total dipole, but they do not radiate, okay? We will find at the end a formula which says the total energy radiated is the sum of those mass multipoles differentiated L+1 times plus, square, plus the spin dipoles also L+1 times square. And because of this, the mass monopole and the mass dipole will not radiate, and the first radiation will start at the quadrupole, okay? But they are there to parameterize the source. Exactly. And then, so, yes, the fact that the first moment that radiates is L equal 2 is linked to the spin 2. Actually, in general, it is the lowest radiated multipole for any spin S is S, okay? For electromagnetism, it is dipole. For gravity, it is L equal 2. If a spin 3 existed, it would be L equal 3. Okay.
Other questions? See, so let's thank again Thibault.
Più che altro perché noi